Thank you, Philip, and thank you for organizing this webinar. What I'm gonna follow up on some of the issues that Philip brought up on, and basically what I want to talk about a little bit today is the urban evolution of water pollution. And so Philip brought up the watershed issues, their importance, how hydrology changes and its impacts to coastal zones. And so many of these issues occur in urban areas. And so urban areas, currently about 60% of the world's population lives in urban areas, and that percentage is expected to grow in the future as people move and live in urban areas. And those urban areas typically are located within 100 kilometers of a coastal zone. So the idea of urban evolution is that basically cities evolve over time. So as Lisa Regain talked earlier today about trying to figure out sustainability issues based on past technologies, what worked and what didn't work, cities are always changing in their infrastructure. And as Philip just mentioned, forecasting is a big issue. We're always interested in what's going to happen in the future. Well, one way to look at what's going to happen in the future is by studying the past, and particularly looking at how the structure, function, and services of cities have changed over time. And depending on how we manage these, they can result in losses of ecosystem functions and services or progress towards restoration. One really good indicator of urban evolution is the chemistry of water. So if you went into your doctor or a hospital and they looked at your blood chemistry, they would be able to tell you, what was your past diet? What are your sodium levels? What are your cholesterol levels? And then based on that, they could tell you if an intervention is needed, if you need to be on some kind of medication to lower cholesterol or change in diet. And after that intervention, you could then look at your blood chemistry and see if it worked or if it didn't work or areas for improvement. So the idea here is that urban cities and urban watersheds evolve over time in ways that can be tracked over time. And you can look at the chemistry of the water to look at these changes in management over time and understand how things are changing in the future. So I want to just briefly discuss 3 examples related to the nitrogen cycle and nitrogen pollution and some changes in technology that have changed the nitrogen cycle in urban waters. Then I want to talk about something that related to how humans have accelerated the weathering process. And the reason why this is important is in a number of talks today, we've talked about Flint, Michigan and the water issues. And so we have some pretty robust changes happening throughout big areas of the United States related to the chemistry of water, related to alkalinity, to dissolved salts in the water from the accelerated weathering of rocks due to decades of acid rain. And I want to talk about that and some impacts it has on larger rivers, and particularly those rivers that are used for drinking water supplies, because those salts can interact with pipes and influence corrosivity as well. And the last thing I want to talk about is salinization, which is a related issue to this weathering issue, but from road salts and some of the impacts that has, and some implications for water and watershed processes. So we'll talk about the nitrogen cycle, weathering, and salinization, and how things are changing, basically the processes underlying these, and what that might mean for non-point source pollution in the future and water supplies. So there's been evolving sanitary infrastructure over time. That's one of our successes in managing the nitrogen cycle. You can see a picture of Blue Plains wastewater treatment plant. I took this picture from a plane flying over DC a couple years ago, and at the Blue Plains treatment plant, which discharges to the Potomac River, which you can see in the background, they've implemented state-of-the-art technologies in nutrient control and nitrogen removal through denitrification. And as a result, you can see that nitrate concentrations in the effluent have decreased over time in their effluent using these different strategies. And so this is one example of how technological changes over time can result in changes in the chemistry of water and effluent discharge to rivers over time. And so one thing we've been working on, this is a paper that's actually just recently been accepted for publication, working with DC Water, collaborating with Sudhir Murthy at DC Water and a graduate student, Michael Panino, who now works for the EPA. Basically, this was a study looking at how those historical changes over time in infrastructure and nitrogen sources to the Potomac, how that affects the spatial evolution of nitrogen pollution in the Potomac over time, and how far the wastewater from DC, from Blue Plains goes along the Potomac into the Chesapeake Bay. And so what you can see is an X for the wastewater treatment plant for Blue Plains, and then the watershed, and then different sampling stations along the Potomac where cruises were made to look at the sources of nitrogen using stable isotopes of nitrogen, which are like a fingerprint that allows you to tell where the nitrogen's from. And so this is a little bit of a complicated figure, but basically along the river, you can see the nitrogen 15 content of the nitrate is related to how where the nitrogen comes from in terms of wastewater treatment. So you see a very big spike in the wastewater treatment at the distance 0 where the wastewater treatment plant is, and then that signal from the wastewater treatment plant disappears within the first 30 kilometers in the along the Potomac River. And so by looking at these spatial trends and then trends over time, Michael Panino was able to figure out that the spatial plume from the Blue Plains treatment plant has changed over time, and it's shrunk over time in the river, and that also typically we focus on inorganic nitrogen or nitrate pollution, but that organic forms of nitrogen and organic matter within the river was becoming more of a problem, so that the river was taking up the nitrate from Blue Plains within the first 30 kilometers and then turning it into these organic forms, which we know less about. So the second thing I want to talk about is weathering of watersheds. And so when you think of cities, you don't think of cities creating their own geology. You think of the built infrastructure and maybe the engineering of the city. The cities have a very distinct geology. They're made out of concrete materials, cement, asphalt. Many of these materials break down over time, and even concrete lined pipes. And so you can see this is a picture that we took underneath a bridge in Baltimore. And you can see these urban stalactites that have formed where the water basically dissolves the infrastructure, and then there's reprecipitation forming this stalactite formation. And so cities create a distinct urban geology, and it's we call this the urban karst, and it's similar to landscapes in Florida, which are referred to as karst, where it's limestone, where water can dissolve the limestone and then create fissures and cracks in the bedrock. So we've looked at a study which looks at, we were very interested in what water quality impacts this might have. And so we looked at these different sites all along the eastern United States, urban areas, or mostly some areas that were mostly forested. We looked at sites that span watershed size, elevation, lithology, and land use. And these dissolved materials that we easily apply to the landscape, like agricultural limes or building materials, we were wondering if they might have an effect on the water chemistry and something related to water quality. What we found is that about 2/3 of the sites showed increases in bicarbonate alkalinity, including the Potomac River, and there were no decreasing trends in alkalinity. And there were also increasing trends in some of the dissolved minerals like calcium and other byproducts of weathering. And the reason why this may be important is because typically when people think of alkalinity, they think of buffering capacity and that it may be good for water quality. The alkalinity is related to the pH of water, and so if you have increasingly alkaline waters that are discharged that go into larger rivers, it can affect ammonia toxicity in some cases, and then also you have all the other dissolved constituents of the weathering process, like the calcium, magnesium, potassium. Those ions, which can also influence corrosivity. So there's some issues associated with this weathering beyond acid neutralization that get into the corrosivity of water, the types of minerals that are released along with the bicarbonate during the weathering and dissolving of bedrock, along with all the concrete, cement, and building materials and agricultural lime that we apply to watersheds. So these were watersheds where the geology actually wasn't, there was no natural carbonate geology in these watersheds. These are mostly urbanized watersheds, the Patuxent River in Maryland, the Saddle River, and the Baltimore drinking water supply in Maryland. And you can see here that not only is alkalinity increasing, but there's increasing mineral content in the water as well, as you can see with the calcium. So the reason why we became interested in this project in the first place was I was visiting my father-in-law in New Jersey, and we would drink water at his house, and there was always a thin white film on the glasses. And at first I thought this was just the detergent, that it wasn't getting completely clean. But then, I scraped some of it off, and we did some analyses in the lab. And this thin white film that you see around the glass was a residue, basically from all the dissolved minerals in the water. And we have this, whether you're in Maryland, in Baltimore or Washington, D.C., or any major city along the eastern United States. And so, this increased dissolving of bedrock, and then also these bridges and roads, that can affect water quality in these interesting ways that affects the basic fundamental properties of the water in terms of alkalinity and mineral content. So the last thing I want to talk about is salinization, which is another issue that's related to what's dissolved in the water. So we've done a pretty good job with nitrogen and phosphorus and best management practices and looking into these sources. But there are these other non-point sources of pollutants as well, such as road salt, which we may need to think about. And so this is road salt crystals that you see that are actually along the road, and then they lead into a storm drain that goes into one of Baltimore's three drinking water reservoirs. So you can see that there's a direct conduit of this road salt down the drain into the drinking water supply. And so this was this was from a graphic from a paper that was published this year, and the title of the paper was "Increased Salinization Decreases Safe Drinking Water." So it was something that I felt like it needed to be out there, and I'll explain why. So typically, if you go to places in the eastern U.S. or the Midwestern U.S., you can see these increasing trends of sodium and chloride in freshwater ecosystems. And so this is not only a local problem, but it's also a regional problem, and it's also distributed around the world as well. So all these anthropogenic salt inputs, whether it's from road salt or sewage inputs, sewage leaks, water softeners, etc., they increase the salinity of the water. And it turns out that sodium and chloride are very robust universal tracers of human fingerprints on water supplies and the water cycle. And so given that there are these increasing trends, in this paper, Increased Salinization Decreases Safe Drinking Water, the point of the paper was that this may, in some cases, be of interest to people on dialysis or with health issues, but really the interaction between the saltier water and the infrastructure, whether it's concrete or pipe material, the corrosivity aspects are something that we need to pay attention to. And when you have increased salts in the water, they can affect the corrosion potential. And as I mentioned before in the previous case with human accelerated weathering, those weathering products that are being dissolved, from rocks and from concrete, et cetera, they further add to what we're seeing here in terms of, issues maybe related to corrosivity. So, this was a figure from some work that we did in collaboration with Bill Stack at when he worked for the city of Baltimore. And it shows mean annual chloride concentrations on the vertical axis, and then the percent impervious surface cover in the watershed on the horizontal axis. And this is the mean annual chloride concentration, so it's not taking into account the spikes that we see during winter snow events. In some cases, those spikes can reach up to a quarter to a third the salinity of seawater. They get very, very high in some of these streams. But this is just the mean annual chloride concentration. And so at about 30% impervious surface, there's toxicity to most land plants. And then as you get up in impervious surface, it can lead to toxicity of freshwater life. But some of our recent work has shown that beyond these issues related to land plants and freshwater life, there's also the potential for these salts to mobilize nitrogen and phosphorus from sediments to streams. And so what happens is the salt actually displaces the nitrogen and phosphorus from the sediment through ion exchange, and then can lead to increased nitrogen and phosphorus pollution as well. So this is something that we need to think about. Not only are there issues associated with the pipe material and displacement of reactions occurring in pipes, but also in soils and sediments where you get this mobilization of nitrogen and phosphorus to fresh water. So in summary, the urban evolution of water pollution is linked to changes in structure, function, and surfaces over time. I think salinization and alkalinization are these emerging concerns, non-point source pollution, that are difficult to regulate. It often, people recognize them at a local level, but they're pervasive problems in urban areas and then throughout much of the eastern United States and midwestern United States. Tracking urban evolution allows the transition from reactive management to predictive management, where most of our management usually occurs after the fact, after we recognize there's a problem. And looking at these long-term trends allows us to move towards predictive management, where we can understand that a problem is emerging and it's occurring, and then do something about it before it costs us a lot of money or problems down the road. And this salinization and alkalization issue is not going away. It's happening through geological processes and then human inputs of salts. And it's something, the salinity of water is very critical for many of the services that water provides us, and is related to water quality issues and reactions that take place in aquatic environments. So I just wanted to end with that, and thank you for your time.